Ever wondered how a soft gray powder turns into the backbone of our cities? Every skyscraper, bridge, dam, and even the pavement under your feet depends on one material: cement. But cement isn't just dust in a bag, it's a precisely engineered chemical product, designed at the molecular level, which becomes rock solid when mixed with water. Today on Knowledge Hub, we're breaking down exactly how cement is made, and more importantly, what gives it its incredible strength. Everything starts with limestone. Massive quarries extract limestone, which is primarily calcium carbonate, or CaCO. But limestone alone isn't enough. Manufacturers blend it with clay or shale, which supply silica, alumina, and iron oxide. These raw materials are crushed and ground into a fine powder called raw meal. Precision matters here. The chemical composition has to be tightly controlled because even small variations affect the final strength of the cement. Next comes the heart of the process, the rotary kiln. This enormous rotating steel cylinder, often over 60 meters long. It heats the raw meal to temperatures around 1,450 degrees Celsius. Inside the kiln, a series of complex chemical reactions occur. First, calcination takes place. Calcium carbonate decomposes into calcium oxide and carbon dioxide. Then, at even higher temperatures, the calcium oxide reacts with silica and alumina to form new compounds. These compounds fuse together into marble-sized nodules known as clinker. Clinker is where the real magic happens. It contains four primary compounds: tricalcium silicate, decalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. Among them, tricalcium silicate is the superstar. It's responsible for early strength development when cement reacts with water. After leaving the kiln, the clinker is rapidly cooled to stabilize its crystal structure. Then it's ground into a fine powder. During this grinding stage, a small amount of gypsum is added. Gypsum controls the setting time by slowing down the reaction. Without it, cement would set almost instantly. Now here's the real science. Strength doesn't come from drying. It comes from hydration. When cement is mixed with water, a chemical reaction begins. The most important product of this reaction is calcium silicate hydrate, often abbreviated as CSH gel. This microscopic gel forms a dense, interlocking network that binds sand and aggregates together in concrete. The more CSH that forms, the stronger the material becomes. As hydration continues over days, weeks, and even months, the structure becomes increasingly compact. That's why concrete gains strength over time. Proper curing, maintaining moisture and temperature, allows these hydration reactions to continue, maximizing durability and compressive strength. But there's another side to the story. The calcination process releases significant amounts of carbon dioxide, making cement production responsible for roughly 8% of global carbon dioxide emissions. That's why engineers are developing alternatives, like supplementary cementitious materials, fly ash, slag, and calcined clay, to reduce the carbon footprint while maintaining strength. So the next time you walk past a skyscraper or drive over a bridge, remember, cement isn't just a gray powder. It's the result of controlled geology, high-temperature chemistry, and microscopic crystal engineering, all working together to create one of the strongest materials in human history. If you have enjoyed learning how the world is literally built, make sure you subscribe to Knowledge Hub for more deep dives into the technologies shaping our future. And as always, stay curious.